A very good afternoon to all of you. Am I audible?
Good afternoon. Yes, sir.
Okay. So today we'll discuss about the propagation of electromagnetic wave in different mediums. So in connection with that wave propagation in different medium, we have to derive the wave equations. We have to discuss on skin effect, skin depth, and finally we'll discuss about the energy conservation laws, that is the Poynting theorems, and some related problems that will be discussed on today's class. I'm going to share the today's presentation. Is the PPT visible from your end?
Yes, sir.
Yes, sir.
So hope most of the students have joined. So I am starting the class. Now when we are talking about the electromagnetic wave propagation in free space or in some medium, we have to talk about the two different fields which consist the electromagnetic wave. So we will consider the electric field and magnetic field one by one. Now if we consider an electromagnetic wave, that is the electric field of the electromagnetic wave, we can write the equation of the electric field that is propagating into the free space by these particular equations. In the latter half of this today's class, we will see that how we can derive these particular equations. But at the starting, we are considering the equation of the electric field in free space, that is E equal to E0. E0 is the amplitude of the electric field. Cos of omega t, omega is the frequency, omega t minus beta z, where beta is representing the phase constant and z is representing the direction of propagation of the electric field. And this ax is representing the amplitude of the electric field, and x is representing that the electric field is along the x-axis. That is, we are considering the x component of the electric field. So by this type of equation, we can represent the electric field in a free space E equal to E0 of cos of omega t minus beta z into the unit vector ax, where omega is the frequency, beta is the phase constant, and z is representing the direction of propagation. So simply from this equation, if I ask that what is the direction of propagation of the electromagnetic wave, from this particular notation, that is beta z, so there is a z, so you will say that the electromagnetic wave will propagate in the direction of z, positive z direction. And this ax representing that, this is representing the x component of the electric field. Similarly, we can represent the magnetic field in free space by this equation. Similar type of equation, H equal to H0. H0 is the amplitude of the corresponding magnetic field, cos of omega t minus beta z, Ay. Ay is the unit vector. That means it is representing that the magnetic field, we are considering the y component of the magnetic field, so that the electric field and magnetic field, they are perpendicular. Electric field is along the x-axis, magnetic field is along the y-axis, so they are perpendicular with each other. Combinedly, they are forming the electromagnetic wave. Now this minus sign is representing that the wave is propagating into the positive z direction. If we consider in the equation that is plus sign, That means the wave will propagate in the minus z direction. So we can represent the corresponding wave in that way. This is x-axis, this is y-axis, this is the z, that is the direction of propagation. So as per our equations, we have considered the x component of the electric field. So this orange color plot is representing the electric field which is along the x-axis, and it is propagating into the z direction. Next, as per the equation of magnetic field, we have considered the y component. So you see this blue color plot, it is representing the magnetic field which is in the y-axis, along the y-axis. That is basically the y component of the magnetic field. So this electric field and magnetic field, they are perpendicular with each other and they are propagating in the positive z direction. So that is the situation when we are considering the electromagnetic wave propagation into the free space. There is no loss, there is no attenuation. We can represent the equation in that way. But if we consider the wave propagation in some medium, then we have to consider the effect of the medium, and in that case we have to include the attenuation factor, that is known as this particular term e to the power minus of alpha z, where alpha is representing the attenuation constant. So if you compare with the previous equation of the electric field, only this term e to the power minus alpha z, it is the new one that is introduced into the equation of electric field in free space, because as we are going to discuss the electromagnetic wave in a particular medium, so we have to include the attenuation factor. So along with the previous equation, only this e to the power minus alpha z term is included, where alpha is the attenuation factor or attenuation constant. So similarly, magnetic field can be represented by H equal to H0 e to the power minus alpha z. The rest of the part is same, cos of omega t minus beta z ay. So we are considering the x component of the electric field and y component of the magnetic field. And now in that case, as we are considering the electromagnetic wave propagation in a particular medium, so we have introduced the attenuation factor e to the power minus alpha z. Now if we draw the corresponding field, what will happen? Once again, this is the x-axis, this is the y-axis, this is the z-axis, that is the direction of propagation. So we are considering the x component of the electric field by this orange plot. Now this electric field, as it is moving towards the positive z directions, it is attenuated. Its amplitude is attenuating. Similarly, the y component of the magnetic field, that is along y-axis, as it is moving towards the positive z direction, its amplitude is decaying or attenuating. So that is the situation in terms of electric field and magnetic field separately, if we consider their propagation in the free space and in medium. When we will consider the propagation in a medium, we have to include the attenuation factor. Now the question is how we are getting these equations, that is the equation in free space and equation in medium, that will be discussed one by one. Sorry. Now, before starting the derivation of wave equations in free space or in some medium, we will discuss about the time harmonic field, because we have considered the electric field and magnetic field as the sinusoidal one, and we have seen that when it is entering into some medium, its amplitude is attenuating. So we have to concentrate on that, or we have to discuss about the time harmonic field. Time harmonic field means basically it is varying periodically or sinusoidally with respect to time. The next point, that is how we can represent the phasor, or what do we mean by phasor? Phasor means it is nothing but a complex number that consists of the amplitude and phase of the sinusoidal signal or sinusoidal oscillation. And as you know, how we can represent a complex number? Simply z equal to x plus jy. So this phasor or the complex number z can be represented by z equal to x plus jy, that is equal to r of angle phi. That means, or in other way, we can say that z equal to r of e to the power j phi, that is equal to r of cos phi plus j sin phi. I think these things are known to you from the mathematical background. So this is the graphical representation of the corresponding phasor r. This is the x component, this is the y component. The angle between the r and x is phi, and this is the omega is the angular frequency. So from this complex representation of the phasor, we can say that r means that is nothing but mod of z, that is equal to root of x square plus y square. What about the phi? Phi equal to tan inverse y by x. So with this basic idea on the time harmonic field, that is varying sinusoidally with respect to time, we can represent it with the help of a phasor or a complex number in that way. That is z equal to r of e to the power j phi, where r equal to root of x square plus y square and phi equal to tan inverse y by x. Now in general, if we say that whether phasor is a scalar or vector, your answer will be phasor may be scalar or maybe a vector. So if a vector, that is a time varying vector a, xy with respect to x, y, z and time, so its time harmonic phasor is, the phasor is represented by a of s. These two quantities, that is the corresponding vector and its phasor, are related by this relation, that is vector a equal to real part of the as, that is the phasor of the vector a, into e to the power j omega t. Now, for example, if we consider that the vector a equal to a0 of cos omega t minus beta x into a y, that is the vector is along the y axis, or we are considering the y component of the vector only, then from this equation 8.67 we can write down that what will be the vector a equal to real part of, only in place of as it will be a0 of e to the power minus j beta x, a0 of e to the power minus j beta x into e to the power j omega t as it is. So if you compare this 8.67 and 8.68, if you compare these two equations, you will find that what is as, that as is nothing but as equal to a0 e to the power minus j beta x ay. So that is the relation between a vector and its corresponding phasor. Now if you consider the time derivative of equation number 8.67, that is del a of del t, del a of del t, that is the real part of as e to the power j omega t. So it becomes real part of the j omega as e to the power of j omega t. Now if we compare this with the equation number 8.67, so you can say that, or you can see that this time derivative of the instantaneous quantity, or the time derivative of the vector, that is equivalent to the multiplying the phasor by j omega t, that one. Del a of del t, that is nothing but j omega of as. Okay, so with this particular discussion, it is established that the time derivative of a vector or of a quantity is nothing but that will be equal to the multiplying the corresponding phasor by the term j of omega. That is, if we find that there is some derivative, suppose del e of del t, we can write down that in a phasor form. If we have to write down the del e of del t in terms of phasor form, then we have to write down that j omega of es. So similarly, if we consider the integration of a particular quantity, that is integration of a del t, that will be as by j omega. So time derivative means j omega of as, time integration means as by j omega. That things you need to remember. regarding the phasor representation of any quantity or any vector. That is the time derivative of any instantaneous parameter or vector, that will be j omega of the into the corresponding phasor, and time integration of the corresponding quantity, that will be equal to the phasor divided by the j omega. Now we are already familiar with the 4 different Maxwell's equations. Now we rewrite the 4 different Maxwell's equations in terms of this phasor form, that will be called the time harmonic form of the Maxwell's equations. These equations, that is the first equation of the Maxwell's, divergence of D. Now in place of D, we have replaced it by its corresponding phasor, that is ds. Divergence of ds equal to rho of vs, that is known to us. Divergence of B, now B is replaced by the corresponding phasor from bs, so divergence of bs equal to 0. Now we know curl of E equal to minus del B del T. I think you should remember that curl E equal to minus of del B del T. Now the time derivative, that is del D del T, is now replaced by this j of omega. So it becomes j omega bs. Now you can rewrite this expression in, if you write down b, we know that b equal to mu s, sorry, b equal to mu h. So it will become j omega mu hs. Similarly, the last equation, that is curl of h. Now h is replaced by the corresponding phasor hs, that is equal to j plus del d del t. So del d del t, there is a derivative, time derivative. So the corresponding time derivative is replaced by the j omega. So it becomes js plus j omega ds. Now if you rewrite this equation ds in terms of epsilon e, because we know that d equal to epsilon e, so it will become j omega epsilon es. So these are called the time harmonic form of the Maxwell's equations, which are basically applied when we have to deal with the propagation of the electromagnetic wave. So when we'll deal with the propagation of the electromagnetic wave, instead of considering the normal Maxwell's equations, we have to consider this time harmonic form of the Maxwell's equations. Time harmonic form means, which is nothing but if there is any time derivative, that will be replaced by j omega. If there is any time integration or integration with respect to time, that will be replaced by the 1 by j omega. Okay. So now to derive the wave equations, we have to deal with this Maxwell's equation in time harmonic form. So first we are going to discuss about the wave equations, or to derive the wave equation for the electromagnetic wave. Now the wave propagation means, that is nothing but the transporting the energy or transporting the informations. Wave is transmitted from one point to another point, means we are transmitting the energy or we are transmitting some informations. Okay. So we have to take the help of Maxwell's equations to derive the wave equations in different medium. Now with this basic idea, first we have to concentrate on the different types of medium, that is the free space, lossless dielectrics, lossy dielectrics, and good conductors. Now free space means epsilon equal to epsilon naught, mu equal to mu naught, and sigma equal to 0. Sigma is the conductivity. Sigma equal to 0. Now in case of lossless dielectric, this sigma is also 0, and what will be the mu? Mu will depend on the corresponding relative permeability, that is epsilon r. So mu epsilon equal to epsilon r into epsilon naught, and mu equal to mu r into mu naught. As it is the lossless dielectric, that means this conductivity, that sigma should be much less than omega epsilon. Next, in case of lossy dielectrics, that means there is some loss. If the wave propagates through this particular medium, the wave will be attenuated. So sigma not equal to 0, sigma is not 0, and this epsilon becomes same, that is epsilon r into epsilon naught, mu equal to mu r into mu naught. And for a good conductivity or good conductors, obviously your conductivity will be tends to infinite, sigma tends to infinite, epsilon equal to epsilon 0, mu equal to mu1 into mu naught. And this is the most important point here about the good conductors, that sigma, that is the conductivity, should be much greater than omega epsilon. So for this, if we now concentrate on the lossy dielectrics, for the lossy dielectrics, what are the parameters? Sigma equal to 0, and this sigma equal to much less than omega epsilon. So with this condition for the lossless, what I have mentioned, lossy dielectrics, sorry, for the lossy dielectrics, sigma is not equal to 0, and epsilon equal to epsilon r into epsilon naught, and mu equal to mu r into mu naught. So for this particular point, now we have to consider these equations. Divergence of ES, divergence of DS is there basically in the equation. You can write down in terms of E also. So this divergence of ES will be equal to 0. What about the divergence of B? Divergence of B is also 0. In that case, divergence of D actually rho S by V. Rho S by V. So rho will be 0 as it is the case of lossy dielectric. So these are the time harmonic Maxwell's equations for a lossy dielectric. Now to derive the wave equations in this particular medium, in this particular lossy dielectric, you have to start with these equations. You see this curl of ES equal to, you know that is basically minus of del V del T. Now this time derivative del T is replaced by J of omega. So it's basically J omega of BS. Now the relation between B and H is B equal to mu H. So it becomes minus J omega mu into Hs. What about the curl of Hs? Curl of Hs we know that is J plus del D del T. So in that case, J equal to the conductivity current, that is sigma Es, and del D del T is replaced by J omega, D is replaced by epsilon E. So all these are the modified time harmonic equations for the lossy dielectric medium in phasor form. Now we are taking curl on the both side of this particular equation, that is of equation number 3, or equation number 9.3. Now taking the curl on both sides of these equations, we just simply take the curl on both sides. It becomes curl of Hs on the right hand side. Now we apply the vector identity, curl of curl A. Curl of curl A means grad of divergence A minus grad square A, that you know. Now if you apply this particular vector identity in these previous equations, it becomes this one, grad of divergence of Es minus grad square Es, and on the right hand side it is nothing but J omega mu of curl of Hs. Curl of Hs equal to sigma plus J omega epsilon Es. So basically you have to put the 9.4 and 9.1 in this particular equation. After applying the vector identity in equation 9.5, you have to put the value of divergence of Es and curl of Hs. So you see that this divergence of Es equal to 0. Only on the left hand side it becomes grad square Es. Grad square Es, that is equal to minus J omega mu of curl Hs. Curl of Hs equal to, from 9.4, that is sigma plus J omega epsilon into Es. Sigma plus J omega epsilon Es. So it becomes grad square Es minus gamma square Es equal to 0. This equation number 9.7 is known as the wave equation for the electromagnetic wave in a lossy dielectric, where if you consider the previous equation, you will find out that this gamma square, that is basically known as the propagation constant, or gamma is known as the propagation constant rather. So this gamma square equal to j omega mu sigma plus j omega epsilon. That is, if you compare with the previous equation, this one is basically the gamma square. J omega mu into sigma plus j omega epsilon, that is equal to gamma square. So similarly, you can find out the wave equation in terms of magnetic field also, and it will be like that: grad square H is equal to grad square H is minus gamma square into H is equal to 0. So this equation number 9.7 and 9.9, these are known as the wave equation. Do you have any doubt? You can ask me.
No, sir.
Okay. So this parameter is very important. It will be required in the next few slide also. This propagation constant gamma. Now this gamma is also written in terms of this alpha and beta, where alpha is the, as we have already defined, that alpha is, what is alpha? Alpha is the attenuation constant.
Attenuation constant.
Okay, and beta is the phase constant. So this gamma can be written in the form of alpha plus j beta. So in this from basically from the 9.8 and 9.10, we can note it in that particular form, that is the real part of gamma square equal to basically beta square minus alpha square, that is equal to omega square mu epsilon. From this particular point, you can find out that it will be becomes omega square mu epsilon. So it becomes omega square mu epsilon, and mod of gamma square equal to alpha square plus beta square, that will be equal to this. So now if you solve this equation 9.1 and 9.12, you will be able to find out the equation for alpha and beta. I am not going to to solve these equations. You can check it. If you solve these two equations 9.1 and 9.12, you will be able to find out the equation of alpha and beta in that way. So this equation 9.13 and 9.14, they are representing the alpha and value of alpha and beta. This is the generalized equation. Now we have already mentioned different types of medium: free space, lossy medium, lossless dielectric, good conductors. For different medium, the value of sigma, relation between the omega epsilon are mentioned. So from that point, you can find out the value of alpha and beta for different mediums. Okay. But these are the general equations. You have to remember these general equations to derive the value of alpha and beta for different particular for a particular medium. So previously, up to this basically we have established, or we have find out, derived the wave equation in a lossy dielectric. Now we have to find out the equation of electric field and magnetic field for a lossy dielectric medium. Now if we consider the only to find out the electric field and its phasor is ES. As per our discussion, we have considered only the x component of the corresponding electric field. So if you consider only the x component of the electric field, the phasor can be written in this particular form: ES equal to EXS. It is propagating along the z direction, and we are considering the x component, so AX is the unit vector. So this is the phasor form of the electric field that is along x-axis and it is propagating in the z direction. So E is equal to E of x's z ax. Now you apply the basic wave equation, that is grad square minus gamma square into axs z equal to 0. So grad square of axs, you know, that is nothing but the del to del x square, del to del y square plus del to del z square. Now, as the wave is propagating only in the z direction, so this x component and y component will be 0. And this is only this part, that is minus gamma square into exs. So by considering this phasor form of this wave equation for the electric field, it becomes del to del z square minus gamma square exs equal to 0. Now if we consider the solution of this equation, we can write down the solution of this differential equation with this particular form. Exs z equal to E0 e to the power minus gamma z plus E0 dash e to the power gamma z. As we are considering only the z component, so we can assume that E0 dash equal to 0. E0 dash equal to 0. So from the previous equation, what will be the equation of EZT? That will be real part of E of xz, E of xsz, that is the phasor component, e to the power j omega t into ax. Now in place of E of xsz, E of xsz, you can put, that is E0 into to the power minus alpha beta into z, e to the power minus of alpha, this equation, this particular word, e to the power gamma z. This part becomes 0. The second part becomes 0. So only the first part will remain. Now in place of gamma, you have to put alpha plus j beta. In place of gamma, you have to put alpha plus j beta. So in place of gamma, if you put alpha plus j beta, the terms that contains j, it will be e to the power j of omega t minus beta z. So finally, it becomes E of, that is the electric field that is propagating along the z direction and it is varying with respect to time. So it is E of zt equal to e to E0 e to the power minus alpha z, and for this particular term e to the power j of omega t minus beta z, we can write down in that particular form cos of omega t minus beta z into ax. That was the expression of electric field in a particular medium that we have started in the second slide. This e to the power minus alpha z, it is basically representing the attenuation of the electric field as it moves along the z direction. Okay, so EZT equal to E0 e to the power minus alpha z cos of omega t minus beta z. So similarly, you can also find out the magnetic field component or magnetic field, that is H of ZT. H of ZT will be equal to, like in this particular form, real part of H0 e to the power minus alpha z e to the power j omega t minus beta z. If you rewrite, that will be H0 e to the power minus alpha z cos of omega t minus beta z into AY. Now here, this relation between this H0 and E0, H0 equal to basically E0 by eta. What is this eta? Eta is known as the intrinsic impedance and its unit is ohm. So H0 equal to E0 by eta, while eta is the intrinsic impedance. Now solving these equations, you can find out what will be the value of eta. So eta will be equal to root of j omega mu by sigma plus j omega epsilon. In phasor form, you can write down that mod of eta into angle theta n, or that is e to the power j theta n. So basically, what will be the mod of eta? Mod of eta will be equal to root of mu by epsilon divided by this one, and tan 2 theta will be equal to sigma by 2 epsilon, sigma by omega epsilon. So these are the basically equations. You should check it. So main thing is that starting from the wave equation in a lossy dielectric medium, we have find out the equation of electric field, and magnetic field, and we have seen that there will be a propagation constant, attenuation constant we have to include, that is e to the power minus alpha z. So these are the general equation of wave in lossy dielectric, and this EZT and HZT, they are representing the equation of electric field and magnetic field when it is propagating along the z direction, and it is varying with respect to time, and it is attenuating with a factor of e to the power minus alpha z. Now this attenuation constant, it is basically measured in terms of Nepers per meter. Now the relation between the Neper and actually 1 Neper equal to 8.686 dB. This quantity beta we have considered because the gamma equal to alpha plus j beta, where beta is the phase constant. So if we want to find out the velocity of the wave, that with this equation, by this particular equation, you can find out the velocity of the wave E equal to omega by beta, the angular frequency, by the phase constant, and that is known to you, lambda equal to 2 pi by beta, or simply the beta equal to 2 pi by lambda, and that is the equation of intrinsic impedance in a lossy dielectric. Consider the value of alpha and beta for a particular lossy dielectric, that is j omega mu by sigma. This is sigma. Now once we derive the wave equations and the equation of electric field and magnetic field for a lossy dielectric, now we are moving to the what will be the equation of plane wave in a lossless dielectrics or in free space. So we have already defined all the medium for a lossless dielectric. What is sigma? Sigma equal to 0. What is epsilon? Epsilon equal to epsilon naught into epsilon r. And what is mu? Mu equal to mu naught into mu r. And these are the general equation of alpha and beta that we have already derived. So first we will find out the value of alpha and beta for a lossless dielectric. So if you put all these conditions in the equation of alpha and beta and the equation of u and beta, you will find out that alpha equal to 0. You should check it from this equation. If you put sigma equal to 0, finally you will get that alpha equal to 0. And what will be beta? Beta will be equal to omega into root of mu epsilon. And what will be the velocity? Velocity equal to omega by beta. Now we put the value of beta, so it becomes 1 by root of mu epsilon. What will be lambda? Lambda will be equal to 2 pi by beta. Beta is already calculated. So in that way, considering the condition of the corresponding medium, you have to first find out the alpha and beta. Then from the general equation of the wave equation, so that will be the equation of eta. Then what will be the equation of E and H? Alpha becomes 0. So there will be e to the power alpha of z. E to the power minus alpha z terms becomes 1. So E equal to simply E0 into cos omega t minus beta z into Ax. What will be magnetic field? H equal to H0 cos of omega t minus beta z into Ay. So only the attenuation terms, there will be no attenuation as this is a lossless dielectric. So e to the power minus alpha z terms will be cancelled out. So in free space also, what is sigma? In free space, sigma equal to 0, epsilon equal to epsilon naught, and mu equal to mu naught. So from the basic equation of alpha and beta, you will be able to find out alpha equal to 0 and beta equal to omega root of mu naught into epsilon naught. And this root of epsilon naught, that is basically 1 by root of mu naught into epsilon naught, that is nothing but the velocity of light. So it becomes omega by c. So what will be the equation of u? U equal to becomes 1 by root of mu naught into epsilon naught. 1 by root of mu naught into epsilon naught is nothing but the velocity of light. That's why, or if I ask that, or say you have to prove that, you prove that the electromagnetic wave propagates with the velocity of light in the free space. Then what you have to show? You have to first consider that for the free space, this is the value of sigma, epsilon equal to epsilon naught, mu equal to mu naught. Then you have to consider the equation of alpha and beta. You find out the value of alpha and beta, and you find out the velocity of the corresponding wave. You'll find out that velocity of corresponding wave will be equal to 1 by root of mu naught into epsilon naught. So once you able to find out this particular equation, then you can say that the wave in a free space will move with a velocity of light. Okay. So that thing is mentioned in this particular paragraph basically. So now, so what will be the equations of electric field and magnetic field when it will move in a free space? And before that, what will be the intrinsic impedance? What will be the intrinsic impedance? Intrinsic impedance, we have already find out that is equal to root of mu naught by epsilon naught. Mu naught is 4 pi into 10 to the minus 7. Epsilon naught is 8.854 into 10 to the minus 12. If you calculate it, it will be around 377 ohm or 120 pi. Okay. So for a free space, as mu r equal to 1, epsilon r equal to 1, so the intrinsic impedance becomes root of mu naught by epsilon naught. Now we just put the value of mu naught and epsilon naught for a free space, and you will find out that the intrinsic impedance is 377 ohm. That is also another important question frequently comes, that you just show that or find out the intrinsic impedance of the free space. In that case also, you have to consider this first you have to consider this condition for the free space, because we know that for the free space sigma equal to 0, epsilon equal to epsilon naught, mu equal to mu naught, and mu r equal to 1, epsilon r equal to 1. So alpha becomes this, beta becomes this. Next, what about the intrinsic impedance? Intrinsic impedance, the equation of intrinsic impedance becomes root of mu naught by epsilon naught. Then you just put the value of mu naught and epsilon naught for the free space, and you just calculate it. It will be around 377 ohm. So what will be the equation of electric field? Once again, as sigma equal to 0, alpha becomes 0. So once the alpha becomes 0, so e to the power minus alpha z terms that present both in electric field and magnetic field equation for a particular medium, that e to the power minus alpha z terms becomes 1. So E equal to E0 into cos of omega t minus beta z. That is the x component ax. H equal to A0 cos omega t minus beta z to Ay. So from the wave equation itself, we can say that this wave is propagating along which direction? Along z direction. This is also propagating along z direction. Ax is representing that the electric field is along x-axis, and magnetic field is time varying along the y-axis. Is there any doubt?
No, sir.
Okay. So with this basic discussion, now we will consider the wave propagation in a good conductor. Now for a perfect conductor, we have already mentioned that what will be the conductivity. Sigma should be tends to infinite, epsilon equal to epsilon naught, and mu equal to mu naught into mu r, and this sigma should be much greater than omega epsilon. These are the conditions for a good conductor. So from the basic equation of alpha and beta, now we have to calculate the value of alpha and beta, and we have to also calculate the velocity of the wave, and the corresponding wavelength. Okay. So if you calculate the alpha and beta from the basic equation of alpha and beta, it will become omega mu sigma by 2. Now in place of omega, you can put 2 pi f. If you put omega equal to 2 pi f, it becomes root of pi f mu into sigma. So similarly, you can also find out the intrinsic impedance, and from the intrinsic impedance, you will see that there is a phase difference between the electric field and magnetic field. What is the amount of phase difference? That is 45 degree. So there is a phase difference or phase lag between the electric field and magnetic field, or you can say the electric field leads the magnetic field by 45 degree. As we are considering the wave in a particular medium, that is a good conductor where alpha is not equal to 0. So what will be the equation of electric field? That will be E0 into 2 to the power minus alpha z cos omega t minus beta z into Ax. As we have find out that electric field leads the magnetic field by 45 degrees. So what will be the equation of H? H becomes this one. It is actually H equal to H0, and we know the relation between the H0 and E0. H0 equal to E0 by eta. So it is basically the E0 by eta. This term is nothing but the H0. And we know H0 equal to E0 by eta. So it is basically E0 by eta e to the power minus alpha z cos omega t minus beta z. There is a phase lag. H is lagging behind the electric field by 45 degree. So there will be minus 45 degree. So we have seen that when we are considering the propagation of electromagnetic wave in a good conductor, we have seen that alpha is not equal to 0. So there must be some attenuation of the electromagnetic wave as it propagates into the conductor. And we have seen that there is a 45 degree phase lag between the electric field and magnetic field. So this is the conclusion. As the electric field or magnetic field travel into the conducting medium, its amplitude is attenuated. By which factor? By a factor of e to the power minus alpha z. From this particular point, now we will move into the concept of skin effect or skin as well as the skin depth. So we have seen that as the electric field or magnetic field propagate into the good conductor, they are attenuating by a factor of e to the power minus alpha z. So skin effect is basically explains the energy of electromagnetic wave that stays on the skin or surface of the conductive material. So if we consider the basic equation of electric field that is passing through the conducting medium, we are considering again the basic equation E0 e to the power minus alpha z. So electric field is attenuating by this particular factor e to the power minus alpha z cos omega t minus beta z. Z is the direction of propagation. So we can represent in that way. So this is the free space. This is the boundary of the free space and the conducting medium. This is the boundary. On the left hand side of this boundary, this is the free space. On the right hand side of the boundary, this is basically the conducting medium, but sigma is not equal to 0. Now in free space, what is the equation of electric field? In case of free space, there will be no attenuation factor. So if you draw the corresponding electric field is along x-axis and it is propagating along the z direction. So there will be no attenuation. You see, the time period for which the electric field remains in the free space, the amplitude is constant. The amplitude of the electric field remains constant for the time period for which the electric field remains into the free space. But once it enters into the conducting medium, now we have to consider the attenuation factor. So once the electric field enters into the conducting medium, then it will be governed by this equation. So now the amplitude of the electric field is now decaying or attenuating as it moves into the z direction. Okay. Now a particular distance is mentioned at this particular point. You see. So this is the particular point where on the value of z that is defined by delta. So for this particular length or for this particular depth, the amplitude of the electric field E0, it will be attenuated to e to the power minus 1 value. It will be attenuated to e to the power minus 1 value. That is, it will be attenuated to 0.368 E0. From the maximum 1 E0 to, it will be attenuated to 0.368 E0. Almost 37% decay in the amplitude. So this particular depth is known as the skin depth. So the distance delta that is shown in previous figure. So once the wave enters in this particular distance or penetrates at this particular distance, the amplitude of the wave or the electric field that will be decreased to a factor of e to the power minus 1. So skin depth means that represents a distance along z direction for which the amplitude of the wave will decrease to a factor of e to the power minus 1, that is about the 37% of the actual value. And this particular distance is called the skin depth or penetration depth of the medium. That is, if you start with the basic equation of electric field, it becomes E0 into e to the power minus alpha del. In place of z, we are placing z delta. Okay, E0 E0 into e to the power minus alpha d, and it decreases to a factor of e to the power minus 1. So E0 into e to the power minus 1. So if you solve this equation, delta becomes 1 by alpha. Delta becomes 1 by alpha. Now if I ask that what will be the skin depth for lossy dielectric, then you have to first find out the value of alpha for the lossy dielectric, then you have to use this equation. Okay. So this is the general equation of skin depth or penetration depth, delta equal to 1 by alpha. As we know, alpha depends on the corresponding medium. So for a particular medium, we have to first find out the value of alpha, then we have to find out the skin depth. Now, as we have already find out that what is alpha for a good conductor, we have already find out that alpha equal to this one, root of pi f mu sigma. So for the skin depth, delta will be equal to this 1 by root of pi of f mu into sigma. So that means we can define this particular skin depth in that way. It is the depth. It measures the depth to which an electromagnetic wave can penetrate the medium. Okay. Now, is there any doubt regarding the skin depth or the wave propagation in the good conductor?
No, sir.
Now it is already calculated for a lossy medium. For a lossy medium, we have already calculated the value of alpha, that is equal to root of mu sigma omega by 2. So what will be the equation of delta for a lossy medium? Delta will be equal to root of 2 by this. Okay. So for a particular medium, you can find out the skin depth easily by using these equations. So skin depth is basically representing the distance along the z direction at which the amplitude will decrease to a factor of e to the power minus 1. So till this we have discussed about the wave equations, they are general equations. General equation of wave equations, general equation of electric field, general equation of magnetic field. Then we have find out their equation, the corresponding equations for the different medium, like lossy dielectric medium, free space, and the good conductor. At the last, we have discussed about the wave propagation in good conductor, and we have seen that the electromagnetic wave attenuated as it enters into the good conductor, and when the amplitude of the electromagnetic wave decreases to a factor of e to the power minus 1, that particular depth is known as the skin depth, and this skin depth is defined by delta. So delta equal to 1 by alpha. Now with this idea, now we have to move to the energy conservation of electromagnetic wave propagation. Energy conservation is basically defined by the Poynting, and we will now discuss about the Poynting theorem. Now, as we know, the wave is propagating from one point to another point, means basically the energy is transferring from one point to another point by means of electromagnetic wave. Now this electromagnetic wave, they are basically represented by the Maxwell's equations. To derive the Poynting theorem, we will, once again we will take the help of Maxwell's equations. Basically, these two equations we will consider, that is curl E equal to minus del V del T, curl H equal to J plus del D del T. Now, if we take E dot on this particular equation, that is by dotting both sides of this equation 2 by E, that is E dot curl H. In equation 2, if you take E dot on the both sides, it becomes E dot of curl H equal to J dot E plus E dot del D del T. Now I think there is no need to prove that E dot del D del T equal to half of del T of E dot D. That is from the vector identity, you can check it. E dot del T equal to half of del T of E dot D. So from equation 2, or this last equation of the Maxwell equation, we have taken dot on the both sides. That is E dot, it becomes J dot E plus half of del T E dot D. Now we have to use this vector identity, that is divergence of A cross B equal to, this one. Now in this equation, if we consider A equal to electric field and B equal to magnetic field H, then this equation number 3, you see this equation number 3 can be rewrite in this particular form, equation number 4. H dot curl E minus divergence of E cross H equal to J dot E plus half of del T E dot D. Now H dot curl E, this H dot curl E, how we can find out this H dot curl E? The basic Maxwell's equations, this curl E we have considered, curl E equal to minus del V del T. So now if we take H dot on the both sides of this equation 1, so that means now we are taking the dotting the both sides of equation 1 with H, and we can write down that H dot curl E, H dot curl E equal to, it becomes H dot minus del V del T. So similarly, this H dot of minus del V del T minus, if you take this minus outside of this bracket, so it's basically minus of H dot del V del T equal to half of del D del T V dot H. Now you have to put this in equation number 4. So then equation number 4 becomes this one remaining on the left hand side, that is divergence of E cross H, divergence of E cross H. On the right hand side, that is J dot E plus half of del D del T, half of del D del T, this E dot D, and this for H dot curl E. For H dot curl E, you can write down this one B dot H. So this becomes half of E dot D plus B dot H. So this particular equation is basically the statement of the Poynting theorem. This divergence of E cross H it is basically representing the energy E cross H, or it is known as the Poynting vector also. S, E cross S, H, sorry, E cross H is represented by S, that is known as the Poynting vector or energy flow. So S equal to E cross H. This E cross H is also represented by P also. So in some book it is represented by P also, Poynting vector P, or the Poynting vector is represented by S. So in this particular presentation I have mentioned it by S. So it becomes divergence of S, that is equal to minus del U del T minus J of J dot E. So del U del T means that U is representing basically this term, half of E dot D plus B dot H, where this U equal to half of E dot D plus B dot H. So this is not a vector, rather it is a scalar quantity, and it represents the energy density of the electric field and magnetic field. This is the energy density associated with the electric field. This is the energy density associated with the magnetic field, half of E dot D, half of B dot H. So this equation number 5, it is basically known as the continuity equation, or this is also known as the conservation of energy, and this is the Poynting theorem. Conservation, why it is called conservation of energy, that will be clear. You see divergence of S. S is representing the energy flow or the Poynting vector. So what will be the unit of energy flow or Poynting vector? That will be this joules per meter square per second. So on the left hand side, it is representing the total energy flow. So this total energy flow, what about this total energy flow? That is the rate of decrease of stored electric and magnetic energy. And what about this J of sigma E? Sorry, J of E, that is nothing but the ohmic loss. So this equation 5 is basically representing the conservation of energy. The total energy flow through a volume, that will be equal to the rate of decrease of stored energy minus the rate of decrease minus the ohmic loss. So based on this equation number 5 on conservation of energy, you can now consider the statement of the Poynting theorem. So that particular point is mentioned here. Divergence of S, it represents the net electromagnetic power flowing out of a unit volume. So this divergence of S, it is representing the total power leaving a particular volume. What about this del U del T? It is representing the rate of decrease of energy stored in electric and magnetic fields. What about the second term? That is the ohmic power loss or ohmic power dissipated in the corresponding volume. So depending on these equations, this is the statement of the Poynting theorem. So Poynting theorem states that the net power flowing out of a given volume V, that will be equal to the time rate of decrease in the energy stored within the corresponding volume V minus the ohmic losses. So in graphical form, we can represent it in that way. If we consider this is a unit volume, this is the power in, this is the power out. So rate of the total power leaving the volume, that will be equal to the rate of decrease in energy stored in electric and magnetic field. This is representing the stored electric energy, this is representing the stored magnetic energy, and this is representing the ohmic loss. So the net power flowing out of a given volume V, that will be equal to the time rate of decrease of stored electric and magnetic energy minus the ohmic loss. Now if you have any doubt regarding this statement of Poynting theorem and its corresponding derivation, you can ask me. Otherwise, I will move to the next part.
So can you explain the Poynting theorem, means this statement again?
Yes. Okay, let's start with this particular point. Starting from the Maxwell's equation, we have seen that divergence of S equal to minus del U del T minus J dot E. Now this U means that is half of E dot D plus B dot H. Half of E dot D, what is half of E dot D? That is the stored electric energy. What is half of B dot H? That is the stored magnetic energy. And what is this J dot E? That is the ohmic loss or the power dissipated due to the ohmic loss. Clear? So this particular equation says that and S is the energy flow. So what will be the total energy flow from a particular given volume? That will be equal to the rate of decrease of stored energy minus the ohmic loss. That's why it is called the conservation of energy. Total out of energy flow, that will be equal to the rate of decrease of the stored energy. তোমার যে এনার্জিটা stored ছিল in the form of electric and magnetic field, that is decreasing, and there are some ohmic loss in the system itself. So this total loss, one is the loss in the stored energy, one is the loss due to the ohmic loss. So this total loss will be equal to the total energy outflow. That is the statement of Poynting theorem. The total power leaving a particular volume, that will be equal to rate of decrease of the energy stored in the electric or magnetic field and the minus the ohmic loss. So Poynting theorem states that net power flowing out of a given volume V, that is equal to the time rate of decrease in energy stored within the V. How much energy that was stored in the corresponding volume or area, that is decreasing, and there are some ohmic losses. So this total loss will be equal to the total power output. If we consider this is a particular volume, we are considering some stored electric energy due to the capacitor, due to the inducting effect there are some stored magnetic energy, and due to the resistive circuit there are some ohmic losses. So within this volume, we are considering three things. One is the stored electric energy, decrease of the stored electric energy, decrease of the stored magnetic energy, and along with that, we are considering the ohmic loss. This total will be equal to the power output, total power output. Is it clear?
Yes, sir.
Now, along with this Poynting theorems, now we have to discuss some applications related to this Poynting theorems. So using this Poynting theorem, we can find out the power of the electromagnetic wave, because S, that is equal to E cross H, that is representing the net output power flow. So using the Poynting theorem, we can find out the power of electromagnetic wave. We can also find out the power density. It also explains the power density of the electromagnetic wave. So for example, now in that case, the corresponding energy flow E cross H is represented by P instead of S. It is represented by P. They are same thing, Poynting vector basically. Now, as we are already familiar with the equation of electric field and magnetic field in particular medium, in some medium, that is E equal to E0 e to the power minus alpha z cos of omega t minus beta z plus some angle theta 1. This along x-axis ax, h equal to h0 e to the power minus alpha z cos of omega t minus beta z plus theta 2 into ay. So using this basic equation also, we can find out the equation of P. So what will be the P? Simply the cross product of these two. E0 e to the power minus alpha z cos of, one minute. This is the term for E. This is the term for H. Am I audible?
Yes, sir.
Hello. Okay. Now you see that E0 into H0, E0 H0, e to the power minus alpha z, e to the power minus alpha z. So it becomes E0 into H0 into e to the power minus 2 alpha z. So simply there will be cos of omega t minus beta z plus theta 1, cos of omega t. So this is one term. So it's basically cos c into cos d. And it remains ax cross ay. So what will be the cross product of ax and ay? Tell me.
AZ.
Az. So that will be Az. So now in this equation, basically you have to apply the cos c into cos d. So if you use this equation, you will be able to find out P equal to, that is the power density, P equal to E0 H0 e to the minus 2 alpha z by 2 this of this. Now if you have to find out the average power density, to find out the average power density, you have to integrate it with respect to the time period t. Okay. So to find out the average power density, 1 by t, 0 to t, p dt. Okay, this equation you have to use. Now 1 by t, 0 to t, E0 is 0, e to the minus 2 alpha z by 2. Now the first term, the integration of this first term, that will be 0. What about the second term? It will remain as it is, cos theta 1 minus theta 2. So it will be only t. Now this t and this t will be cancelled out. So it becomes E0 H0 by 2 e to the power minus 2 alpha z into cos theta 1 minus theta 2. So that is basically the equation of average power density that we have find out by applying the Poynting theorem. Now we know this theta 1 minus theta 2. Theta 1 minus theta 2 is basically related with the intrinsic impedance by this equation. Eta equal to E by H, theta 1 by theta 2. It's nothing but the E0 by H0, angle of theta 1 minus theta 2. Now this angle of theta 1 minus theta 2 is basically the theta n. So this equation, this particular equation, it becomes P average equal to E0 H0 by 2 e to the power minus 2 alpha z cos theta n. Now you can write down this equation either only in terms of E or in terms of H. So as we know, this equation is known to us, eta equal to E0 by H0. So what about H0? H0 equal to E0 by eta. So if you put this in previous equation, P average becomes E0 square by 2 eta e to the power minus 2 alpha z into cos theta n. So that is the final expression of average power density that we have calculated from the by applying the Poynting's theorem. Now if we consider for a particular lossless medium, for a lossless medium, we have already seen that what is the value of alpha? Alpha equal to 0. What is the value of theta n? Theta n equal to 0. So what will be the average power density? That is eta square by 2 eta. So E0 square by 2 eta. So that is the equation of average power density in a lossless medium. You have to basically remember these equations. Then for different mediums, by applying the condition for alpha and beta and theta n, you can be able to find out the average power density for a particular medium. So for a lossless medium, P average will be E0 square by 2 eta. What will be its unit? Its unit will be volt per meter by ampere per meter. So the average power will be watt per meter square. Okay, it's basically E0 into H0. E0 is the volt per meter. What is the unit of H? H is ampere per meter, so it becomes watt per meter square. Is there any doubt?
No, sir.
Okay, then we will consider some problem associated with this particular point. The time domain expression for the magnetic field of plane wave traveling in a non-magnetic medium. Remember, it is called non-magnetic medium. So non-magnetic medium means what should be the value of mu r for a non-magnetic medium?
1.
Mu r is 1.
1.
Okay, that point you have to remember. So it is mentioned the non-magnetic medium, so mu r will be 1. Now the equation of the magnetic field is given Hxt equal to 0.5 cos of this. It is Az. Okay, it is not Ax or Ay, rather it is Az and it is X. So now find out the direction of wave propagation. Next, find out the dielectric constant and intrinsic impedance. Then find out the time domain expression of electric field, and finally you have to find out the average power density. So basically a time domain expression for the magnetic field is given for a non-magnetic medium. You have to find out the direction of propagation. So first start with the one by one. What will be the direction of propagation? How you will be able to find out the direction of propagation? Tell me. How you will be able to find out the direction of propagation? I have mentioned several times. Just by observing this equation, you will be able to mention the direction of
So
propagation.
in the x direction, then x is
Yes.
plus x.
Plus x. There is a x is there, so the wave is propagating in the x direction. Hxt equal to this, from this particular point, non-magnetic medium, so mu1 equal to 1. Once again, we have considered the basic equation that is given here, 0.5 cos of this. So now if you consider the basic expression of magnetic field that is propagating in a x direction, it will be H0 e to the power minus alpha z cos of omega t minus beta x to Az. So what will be the direction of propagation? That is in the positive x direction. Now if we compare this given equation with the basic equation of the magnetic field in a particular medium, it is cos of omega t. So omega equal to becomes 6 pi into 10 to the power 8. Omega equal to 6 pi into 10 to the power 8. Now minus beta x. So beta equal to 10. This is H0. It becomes H0 equal to 0.5. So H0 equal to 0.5. So once we find out all these parameters, omega equal to 6 pi into 10 to the power 8, beta equal to 10, H0 equal to 0.5. Next, we have to move to the next point, that is dielectric constant. Dielectric constant means epsilon r and the intrinsic impedance, that is eta. For a lossless medium, first of all, from the equation of alpha and beta for a lossless medium, what is the equation of beta? Beta equal to omega into root of mu epsilon. Omega mu epsilon means mu0, mu r, epsilon naught, epsilon r. Beta is given, beta is 10, omega is given 6 pi into 10 to the power 8. Now mu r equal to 1, So within it becomes root of mu naught into epsilon naught into root of epsilon r. Now root of mu naught into epsilon naught means 1 by c. Okay, so epsilon naught becomes root of epsilon naught becomes 10 c divided by 6 pi into 10 to the power 8. This one is the 1 by c. So root of epsilon naught becomes 10 into c by 6 pi into 10 to the power 8. If you calculate it, it will be around 2.54. So dielectric constant is calculated. Now the intrinsic impedance, we know these equations for a lossless medium. Intrinsic impedance equal to root of mu by epsilon. Now mu means mu naught into mu r, epsilon naught into epsilon r. Mu r is given, mu r is 1, epsilon r is calculated, that is 2.54. Now we just put the mu naught. Mu naught means 4 pi into 10 to the minus 7. Epsilon naught means 8.854 into 10 to the minus 12. If you calculate it, it will be around 236 ohm. Then if we move to the next, this is the next question. The time domain expression of electric field. Time domain expression of electric field. Time domain expression of electric field is E0 e to the power minus alpha x cos of omega t minus beta x plus ay. Now this term is 1 as it is a lossless medium. So only you have to find out this value of E0. To calculate E0, we have to take the help of intrinsic impedance because eta equal to E0 by A0, that is known to us. So what will be E0? E0 equal to eta into A0. Eta is calculated, it is 236. A0 is given from the equation, A0 equal to 0.5. So E0 equal to this 1m8, that is equal to E0. So the time harmonic equation will be E0 cos of omega t minus beta x ay. So it will be obvious in the along y-axis. Now the average power, as per the discussion from the Poynting's theorem, the average power density becomes E0 square by 2 eta. That thing we have already derived. E0 square by 2 eta. E0 is 1 on 8, so 1 on 8 whole square, 2 into eta, 2 into eta, so it becomes 29.5 watt per meter square. So this is one simple example related with the Poynting's theorems, from where we have calculated the dielectric constant, basic equation of the electric field. We have calculated the intrinsic impedance as well as the average power density. So that's all almost. And there are just 2 slides I have added. These things are already discussed earlier. That is the stored energy, whether it is magnetic or electric, that you can calculate it using these equations. You should go through these equations. So all these things are already discussed earlier. I just included these 2 slides. These 2 equations is important. That is the average energy density stored in electrical form and magnetic form. So these are the energy density of the EM wave in terms of electric field and magnetic field respectively. 5 is representing the amount of energy density due to the electric field, that is epsilon naught into E square. This is equal to amount of energy density stored due to the magnetic field, that is equal to B0 square by mu 0. So these equations are helpful to solve different problems. You should go through the equations. So that's all. Now I can say that the most of the part of your syllabus that was assigned to me has been covered. Now, if you have any queries, you can ask me. We have basically started with the basic of vector fields. Then we have entered into the coordinate systems, where we have discussed about the different transformation, that is from one coordinate system to another coordinate system, that was discussed. Then we have entered into the electrostatic field, where we have derived two Maxwell's equations. Then we entered into the magnetostatistics, where we have derived about the two Maxwell's equation, another two Maxwell's equations. And after that, we have discussed about the magnetic Maxwell's equation for the time varying field also. And finally, we have considered the Maxwell's equation in the form of time harmonic field with respect to the phasor representation, from where we have discussed about the wave equations. These are the, you can say, the summary of the most of the part of that is covered by me. I will share the today's class note like the early classes. So you should go through this class. Is there any doubt or any queries from your side?
No, sir. I have a doubt regarding the workshop Viva exam.
Okay, before that, I should mention about the question pattern that will be followed in the final semester exam. Okay.
Okay, sir.
Actually, there will be total 9 questions. Question number 1 is mandatory. In question number 1, there will be total 14 questions, including the multiple choice questions. Hello.
Yes, sir.
Okay.
Yes, sir.
Total 9 questions. Question number 1 is mandatory. There will be total 14 questions in the question number 1, along with some multiple choice questions that are mostly based on the short problems. So you should go through the every details of the most of the modules, so that you can attend all the short problems. And this question number 1 will carry the 20 marks. So from the rest of the 8 questions, you have to attend any 4. Sorry. You have to attend any 6. You have to attend any total. Sorry.
Sir, 5,
5.
sir. Any 5.
Any 5. Total 70 marks. Question number 1 is 20. So rest of the 50. For the rest of the 50, you have to attend any 5. Okay. And in question number 1, that is basically the short answer type questions along with multiple choice options. And there will be, most of the questions will be short problems, short numerical problems.
Sir, in question number 1, there will be choice, or we have to attempt all the 15 questions?
There will be total 14 questions in question number 1. Out of 14,
We have to do any 10.
any 10. 10 into 20, 20 marks. Okay.
Okay,
10
sir.
into 20, 20 marks for the question number 1. From the rest of the 8 questions, you have to attend any 5. In the rest of
Those will carry each 10 marks.
yes, those will carry each
Okay,
10
sir.
marks. In rest of the 8 questions, there will be total 4 questions from my part and another 4 questions from the DGCL part. Okay. In multiple choice question also, half from my section and half from the DGCL section.
Okay, sir.
Now you can ask me what about your doubt regarding the workshop.
Sir, how will be the Viva exam in workshop? Means what will be the topics that we'll have to cover for workshop Viva? Or is it means using the Google Meet or something else?
Using the Google Meet, obviously. In this situation, there is no question of physical exam, physical exam of the labs. Then Viva will be over Google Meet. From my part, I can assure you that whatever you did in your lab, the questions will be from that. Nothing theoretical.
So means oh, so will you take all the Viva of all the students, or SMD sir, you and SMJ sir both means three of you
In
will
the,
take all the
interview mode, all the
students
teachers
Viva?
will be present. In the interview mode, all the teachers will be present.
Okay, sir. Means we'll have to cover 3 practicals, the written
Yes,
of
yes,
3 practicals.
yes.
Okay, sir.
A single examination. Okay, this is not 3 separate examination.
Okay, sir. Yes. Yes, sir.
So, and when we need to submit our electronics workshop soft copies, LNB?
Try to submit it before your theory examination, starting of the theory examination.
Sir, our practical examination is on
Okay, sir.
19th. We are starting it with our practical examinations and then we are going to have a theoretic exam. So before 19th?
Obviously before 19th.
Okay, sir.
Okay, let's take the attendance. Abhishek Kumar,
Present, sir.
someone has text Rodit Misra. See what word. Alongir,
Present, sir.
Anirban,
Present, sir.
Artana,
Present, sir.
Orijit, Orko, absent. Orko Prabhu, absent. Ornov,
Present, sir.
Deep Kumar,
Present, sir.
Gaurango,
Yes, sir.
Shahana, present or absent? Absent. Sayon,
Present, sir.
Tanudip,
Present, sir.
Sabori Bagh, present or absent? Shashwat Das.
Present, sir. Present, sir.
Okay. Shouvik Chatterjee, absent. Sorodip Das,
Present, sir.
Swastik Kumar Ghosh,
Present, sir.
Swastik, Torpul,
Yes, sir.
Tuhid,
Present, sir.
স্যার বলছি সৌভিক চ্যাটার্জি চ্যাট বক্সে অ্যাটেন্ডেন্স
হ্যাঁ দেখলাম
স্যার রনিত মিশ্রা সেও
দুজনকে দিয়েছি রূপকুমার
Yes, sir.
ঐন্দ্রিলা চ্যাটার্জি
Present, sir.
শুভম কুমার গুপ্তা
Present, sir.
শ্রীধর
Yes, sir.
শেখ মাসিবুল অ্যাবসেন্ট অর্ঘ্য অধিকারী
Present, sir.
রনিত মিশ্র তো আছে বললো যে রনিত ইউ হ্যাভ অ্যাটেন্ডেড only 2 classes. উদয় সান্নিগ্রাহী উদয় অ্যাবসেন্ট উদয়ন মন্ডল
Yes, sir.
রাহুল চট্টোপাধ্যায় অ্যাবসেন্ট কি এটা মৃণাল রজক অ্যাবসেন্ট সম্প্রীতি
Present, sir.
অপবৃতা
Present, sir.
ওকে
স্যার
হ্যাঁ
বলছি আমি ওয়ার্কশপে শুধু লাস্টে ট্রান্সফরমারটা করেছি তো স্যার ফার্স্টের দুটো তো আমি করিনি তো
না তোমরা যারা পরে যেটুকু করেছো সেটাই করতে হবে
সরি স্যার আরেকবার রিপিট করবেন
যারা পরে জয়েন করেছো কোর্সে পরে জয়েন করার পরে যেগুলো করেছো একমাত্র সেগুলোই দেবে যেগুলো করোনি সেগুলো কিন্তু ল্যাব নোটবুক ইনক্লুড করবে না
ওকে স্যার
ঠিক আছে সো বেস্ট অফ লাক ফর ইওর ফাইনাল এক্সাম
স্যার আপনার পার্ট থেকে কোনো সাজেশনস বা কিছু
ওই যে বললাম যা পড়িয়েছি ক্লাস নোট ফলো করবে ভালোভাবে
ওকে স্যার থ্যাংক ইউ ওকে স্যার
Thank you, sir.
ওকে বাই
থ্যাংক ইউ স্যার